Hello, viewers. In today's session, we are going to discuss an important problem from Fourier transforms, right? So, in this lecture, we'll see how to find the Fourier transform of a Gaussian function of this form, that is e raised to minus x square, right? And moreover, we'll also see that the Fourier transform of a Gaussian function of this type, that is e raised to minus x square, is also a Gaussian function of this form, that is e raised to minus x square, right? So let us start. So viewers, let us first define the Fourier transform of a function f of x, right? Suppose we have a function f of x and we have to find the Fourier transform of f of x. So the definition of Fourier transform of f of x it goes like this. The notation is capital f of x, and here we have the integral minus infinity to infinity. Then we have here f of x, then we have e raised to minus isx dx, right? And where we have the usual notations. So here f of x is the function for which we have to find the Fourier transform, and I is the complex number, that is I square is equal to minus 1, and s is the parameter which may be a real one or a complex number, right? So now we have to find the Fourier transform of e raised to minus x square. So let us take this function as f of x, right? So taking f of x as e raised to minus x square here, so the Fourier transform of the Gaussian function e raised to minus x square is now given by the integral from minus infinity to infinity. F of x is e raised to minus x square, then we have e raised to minus isx dx, right? Now here combining these two terms, because the bases are same, so we can add the exponents. So we have minus infinity to infinity e raised to minus x square, and then we have minus isx dx, right? So now let us first discuss about this term, that is minus x square minus isx. So here we have minus x square minus isx. So we can take the negative sign common. So we have x square plus isx, right? So now let us express this term as a perfect square. So let us write here x plus is over 2 whole square, right? And then here we can write is over 2 whole square. So here what we have done, see, we have used this identity, that is a plus b whole square, that is a square plus b square plus 2ab, right? Now a is x and b is is over 2, right? So b is is over 2. So when we expand this term, then we can easily have here x square, then we have a square plus b square, that is is over 2 whole square, then we have 2 times 2ab. So we have 2 times x times is over 2, and then here we have negative of is over 2 whole square, right? And we can see that these two terms get cancelled, and here we have 2 and 2 get cancelled. So we are left with the same term, that is x square plus xis, right? So these two terms are same, right? So writing x square plus isx like this, because we have x square, then we have 2ab, so 2 and 2 get cancelled, so we are left with isx, and then the term b square, that is is over 2 whole square, may be eliminated by subtracting a term is over 2 whole square. So now multiplying these two terms by with this negative sign, we have minus x plus is over 2 whole square, and then we have minus minus plus, and here we have I square s square over 4. So we can now write I square as minus 1. So we have now minus x plus is over 2 whole square minus s square over 4, right? So now this integral can be written as minus infinity to infinity e raised to, and this term may be replaced by this one. So we have minus x plus is over 2 whole square, then we have minus s square over 4 dx, right? Now splitting this term at this point, we can now write minus infinity to infinity e raised to minus x plus is over 2 whole square, and then we have e raised to minus s square over 4, and here we have dx, right? Now e raised to minus s square over 4 is independent of x, right? Or we can treat it as a constant, so we can take it outside the integral sign. So we have e raised to minus s square over 4, then we have minus infinity to infinity e raised to minus x plus is over 2 whole square, and here we have dx, right? So now the Fourier transform of e raised to minus x square is given by this term which we have written over here, right? Now to evaluate this integral, what we have to do, we have to make use of the method of substitution. So we'll write this term as t, right? So we'll take t is equal to x plus is over 2. So making this substitution x plus is over 2 as t, so differentiating both sides with respect to x, we have dt over dx is equal to 1, because the derivative of x is 1 with respect to x, and the derivative of is over 2 is 0, being a constant. So we have dt over dx, right? And moreover here the value of x, it varies from negative infinity to infinity. So we can easily conclude that when x tends to minus infinity, then t also tends to minus infinity, and when x tends to infinity, then from this relation we can write t tending to infinity, right? So now we can write this integral as we have the term e raised to minus s square over 4. We have minus infinity to infinity. Then we have e raised to minus t square, because x plus is over 2 is t, and dx is replaced by dt, right? So now from the theory of integrals, we know that the value of the integral from minus infinity to infinity e raised to minus t square dt is equal to square root of pi, right? So this is a very standard integral in the theory of integrals. So the value of this integral may be replaced by square root of pi, right? So now we can write e raised to minus s square over 4, and directly applying the result, we have here square root of pi, right? So the Fourier transform of e raised to minus x square is given by square root of pi times e raised to minus s square over 4, right? And we can easily see that the Fourier transform of a Gaussian function is also a Gaussian function, right? Because here we have the original function as e raised to minus x square, and here in the Fourier transform we have e raised to minus s square over 4, right? So we have identical functions in the original function as well as in the Fourier transform, right? So we can finally conclude that the Fourier transform of a Gaussian function is again a Gaussian function.